Hello, we are Team BobaBee and we are going to present LiDAR-based lane navigation. I'm Kevin.
I'm Brian.
I'm Steven.
I'm Ian.
The reason we chose LiDAR-based navigation is because of its longer range and robustness to lighting condition. As shown in the figures, LiDAR has a clearer view in dark environment, and not to mention, it can also give a more precise coordinate for each point in the point cloud.
Let me briefly walk you through our pipeline. Our raw LiDAR points are passed through a pre-process and filtering step, which helps reduce our inference time. It is then fed into our point transformer model to perform real-time inference of lane lines. Simultaneously, the raw points are passed through the KISS-ICP algorithm for post-estimation. These two results are then matched by sequence frame, and the buffer map is created, which is further utilized in our lane detection algorithm to generate waypoints. The waypoints are then utilized in our control unit to determine the steering and acceleration of the vehicle.
For the point transformer model, we trained on 7 different models, where first 5 are using the near IR attribute from the Oster LiDAR, and the last 2 are using the signal value. As for the training data, we trained on 1500 LiDAR frames, where it consists of different lighting conditions. As for the testing on the model, we tested on 681 frames using the signal attribute model, and we obtained a precision of 0.62 and a recall of 0.73. This is the raw data from the Oster LiDAR with signal attribute. What we are trying to do is to extract the lane line information from the point cloud. This is our road line inference result after passing in the raw LiDAR point cloud into the transformer. As you can see, our model is able to segment the lane line precisely.
A key challenge we faced was maintaining lane detection during turns, where the sensor's blind zones can cause us to temporarily lose sight of lane markings. To address this, we implemented localization and mapping solution using point-to-point KISS-ICP algorithm for odometry estimation. We combined this with sequence matching with the inference results in order to transform the local inference result coordinates to its global position. Here's a short video showcasing the trajectory of the vehicle as well as the inference results transformed to its global coordinate. This trajectory and pose is also used in our control unit to determine whether the next determined waypoint is reached by comparing the position of the waypoint with the odometry of the vehicle. We leverage this odometry to implement a buffer mapping system that maintains a short history of previous frames. By tracking our global position through KISS-ICP, we can properly align and combine multiple LiDAR frames into a global map. This buffered approach typically maintains around 20 frames of history, giving us a more complete view of the environment and helping us overcome the blind zone challenge.
As the buffer solves the problem of the blind zone, the vehicle can now locate the lanes nearby. Afterward, we pass the buffer into DB-scan to cluster each point according to their lanes. Then, the right lane points are retrieved to generate the waypoints using window search method. As you can see, waypoints are generated in front of the vehicle to achieve real-time immediate control.
For control, we use the waypoints provided by the generator. Then we select the most suitable waypoint as a target point. Based on the target point and the current vehicle pose, we calculate the required control values, including the steering angle and the acceleration. This is a demonstration under normal daylight conditions. We successfully achieved smooth control, completing half a lap in 1 minute and 50 seconds. This video showcases our project's robustness under low-light environment, where we completed half a lap in almost the same amount of time. Notably, our algorithm was tested on both E2 and E4, achieving comparable performance on both.
To conclude our current work, we have identified 4 main novelty points. First, our use of LiDAR allows us to increase our range of detection and maintain strong performance in low light conditions. Second, our buffer mapping approach increases robustness and effectively addresses the blind zone challenge. Third, our utilization of point transformer V3 allows us to deal with noisy signal data and achieve more accurate lane line detection. Finally, since point transformer model is designed for semantic segmentation, our pipeline can be easily extended beyond just lane detection. By retraining the model with additional semantic labels, we can detect and classify various road elements like obstacles, stop signs, and other traffic features.